Okie dokie, so we're in focus, and I said that I would do little videos to help you prepare for the upcoming test. So I'm going to do a video for each section, 5.1, 2, and 3, and right now this is a video on section 5.1, critical numbers, local extreme values, and the first derivative test. Okay, so the first thing we need to be clear about is critical numbers, so I'm abbreviating it CN. So critical numbers occur when the derivative of a function at some point equals to 0, or when the derivative at that point does not exist. Okay, and I've got the book here because I did show this in class, so in case you missed it or you weren't there. So it's going to get a little weird here for a second, but this is on page 256 of the book. And what we need to look at here, make that a little bit bigger, is this is some function f here, okay, and we want to, examine what's going on here. So if this is f, I want to examine the derivatives of this function, and I don't have a pencil handy, but I know, for example, the smooth bumps, right? So I'm going to have a zero. The derivative is going to equal to 0 here at c sub 1. It's going to equal to 0 here at c sub 3. It's going to equal to 0 here at c sub 6. It's going to equal to 0 here at c sub 7. Okay, so I know that those are going to be critical numbers. And in fact, if I look over this little neighborhood or this interval from, whatever this is, this x or c value, this x value all the way to the end of the function, let's just say, I have, a minimum here and a maximum there, and I've got another min here and a max and another min, and that's neither, but anyway, in this little interval here, I've got a couple of maxes and mins, okay? And so we call those local or relative extrema, or local or relative maxima or minima. Okay, so the places where the derivative equals to 0 is we're going to have our maxes and mins if our function goes from decrease to increase or increase to decrease. Notice here at this sharp corner, the derivative doesn't exist, but this function has a local minimum at this point. Also at this cusp or sharp corner, it's a high point in this little interval, and so it's also a local maximum. So we've got 3 local minima and 2 local maxima at C1, C3, C4, C5, and C6. Okay. And if you look just below, so I can't fit it all in that good, so I'm just going to focus on the picture and I'll read to you what it says. It says that x equals to c7, so the derivative equals 0 there, but it's not a local max or min, sort of a little flat spot there in the graph. And at c2, now if I draw a tangent line here, it's going to be vertical, so that means the derivative's not going to exist at that point. So just because the derivative is 0 doesn't mean we're going to have a max or min. Things have to happen. In other words, signs have to change in order for that to happen. Okay, so what we want to do, because this is a huge part of calculus, is to find local extrema, the max and the min. Okay, and to do that is really quite simple. So let me remove this and let me find a function here in the book, one that I did in class maybe, or oops. So let me fix this. Sorry about it. I'm not the best video person, as you know. But let's just look at, I don't know. Let's just say we have a function f of x equals x cubed minus 3x plus 1. And we want to decide, does this function have any max or minima values over its domain? Okay, so the first thing we do is we're going to take the derivative of the function. That gives us 3x squared minus 3. And you're going to set that derivative equal to 0. Okay, so this is called, by the way, this is called the first derivative test. Okay, you take the derivative of the function that's given, you set it equal to 0, and you solve for x. So if I pull out a 3 here, I'm left with x squared minus 1 equals to 0. If I divide both sides by the 3, it goes away. There's no x multiplied to it, so it's not a problem. So really what I'm looking at here is this. And I know that's the difference of two squares, so we've got x plus 1, x minus 1 equals to 0. And when I solve, I get x is plus or minus 1. So these are the critical numbers, okay? These are the places where f prime of x is equal to 0, okay? And what I'm going to do is I'm going to plot those critical numbers on a number line. And I'm going to test the derivative on the left and the right of each critical number to see what the sign of the derivative is. So for example, if I checked out or tested f prime of negative 2, well, a negative 2 becomes positive. So I have 3 times 4, which is 12, minus 3 is a positive number. So what I know is to the left, or from negative infinity all the way up to negative 1, okay, on this interval or sub-interval, when I plug in a negative 2 into the derivative function, it's going to be a positive number. I don't care what the number is. All I care is that it's positive. So from negative infinity to negative 1, the value of the derivative is positive. Okay. Now I'm going to plug in a 0. So between negative 1 and 1, I want to see what's going on. So if I plug a 0 in to f prime, I'm going to have 0 minus 3. Well, I get a negative number. So what I know is that the value of the derivative, or the derivative takes on negative values between negative 1 and 1. And if I look at the subinterval from 1 to infinity, so suppose I do f prime of 2. So if I plug a 2 in here, I'm going to get 4 times 3 is 12, minus 3 is a positive number. So the first derivative is positive. Now what does that mean? Well, it means I can tell a lot of stuff about the function without a calculator. I know that the function f is increasing from negative infinity to negative 1. I know it's decreasing from from negative 1 to 1. And then I know it goes back to increase again from 1 to positive infinity. And that tells me I have a max here, and I have a min here. So what I'm going to tell my grader is that, I'm going to have a local or relative, I'm just going to abbreviate relative as REL, maximum at x equals to negative 1. And I'm going to have a local or relative minimum at x equals to positive 1. Okay, so without a calculator, I can take a function, take the derivative of that function, set it equal to 0, solve for x, plot those critical numbers on a number line, and test to the left and the right of each critical number to see what the derivative's doing. And then that allows me to determine what the function's doing over those intervals, so I can determine whether any extrema exist or not. Capiche? Now, some of these functions you're going to have to do without a calculator, and some of them get a little bit crazy. So, let's see. I'm looking for one that we did in class. So, number 9 here. This is from page 260. Number 9 has the function f of x is equal to x e to the x. And we want to know, are there any maxes or mins? Okay, so we're going to take the derivative. That's going to be x times the derivative of the second term is e to the x, plus we take the second factor and leave it alone and multiply it by the derivative of the first, which is 1. We set that equal to 0. So we have x e to the x plus e to the x equals to 0. No calculator necessary. I'm going to factor out an e to the x, and that leaves me with x plus 1 equals to 0. Now remember, e to the x, that function, e to the x, looks like this. It's never, ever negative. Ever. Okay? Ever. It's always positive. It's always above the x-axis. So because of that, I know that that's always positive. So really the only thing I need to solve for critical number-wise is right here, and that's easy. X plus 1 equals to 0, so x is negative 1. Okay, so I'm going to make a number line. I'm going to plot my critical number. And now I'm going to test f prime to the left and to the right. So f prime of -2. Oh boy, that's going to give us, so I'm going to write this out. That's going to give us e to the -2 times -2 plus 1. I just want to know, is it positive or negative? E to the -2 is the same as 1 over e squared. That's a positive number. Okay, so even though it has a negative exponent, the number is still positive. So I have a positive number times a negative number. -2 plus 1 is -1. So what I know is that f double prime of -2 is a negative number. So I know that the derivative is negative on that subinterval. And then if I do, say, f prime of 0, well, that's easy, because I'm going to have e to the 0, which is 1, times 0 plus 1. Oops, 1. E to the 0 is 1 times 1, so a positive times positive makes that positively valued. So this is a positive value, so I know my derivative is positive here. And based on that, I know that the function f from -infinity to -1 is decreasing, and then from -1 to positive infinity it's increasing, and it's at the bottom of the bowl. So I would expect a relative minimum at x equals to -1. Now, if for some reason you're asked for the minimum or maximum value, then what they want is the y value. Okay, so in other words, if they want the minimum value, what you're going to do is you're going to take your critical number and you're going to plug it, you're going to plug it back into f of x. So you're going to evaluate f of -1, which is -1 times e to the -1, which is -1 over e. And that's a number, that's an exact number. If I use my calculator to get some kind of a decimal, it's an approximation, okay? So the minimum value would be -1 over e when x is equal to -1. So most of the time they're going to ask you, you know, what values of x do the local maxes and mins occur? So you can just, you know, say at x equals to whatever. But if they ask you for the value, that word value means the y value. That means you need to plug your critical number back into the original function, into f, not f prime, and figure out what the output value is. Okay? That's the first derivative test. It's really quite simple. Now, I say in class all the time, you know, what's the tallest building between MLK and Hillsborough Avenue on Central? And we all say Hillsborough High School, right? So in that little neighborhood, or that little interval between MLK and Hillsborough, the tallest building, or the absolute largest building on the street on Central, is Hillsborough High School. And then there's probably some little house or building or whatever that would be the smallest value. Okay, that would be local max and min on the interval from Hillsborough Avenue to MLK. Okay? If I wanted the absolute highest point in the world, that would be Mount Everest, and the absolute lowest point in the world, that would be the Dead Sea, as far as I know. Then, now I'm talking about global or absolute extreme values. Okay, so we have global, which is also called absolute. They mean the same thing. Extrema. Global max. Oh, this thing is, I don't know why that's happening. Sorry about that. Global maxes or global mins. And you will always be given, you'll be given a function f of x, and you'll be given an interval. And this is, okay, I'm sorry. I don't know why this thing is, let me try again. I apologize. Like, why is this thing not focusing? I don't know. So you'll always be given a function, and you're going to be given an interval. And using that, you're pretty much going to be repeating the first derivative test over, except you're going to test your critical numbers and the endpoints of your interval back into the original function. So it's best done by example. Okay, so let me show you. We have a function. It's x to the 4th minus 2x squared excuse me, plus 3 on the interval from -1 to 2. Okay, I know right away that if it's asking for extrema, I know it's global because I've got an interval now, whereas in the other cases we didn't have an interval, we just had a function. So I'm going to take the derivative, which is 4x cubed minus 4x, and I'm going to set it equal to 0. And I'm going to solve. So if I pull out a 4x, that leaves me with x squared minus 1 equals to 0. So solving this, I know that x is equal to 0 and plus or minus 1. 0 plus minus 1 are in this interval, so I need to test them all. Okay, so once you get your derivative and your critical numbers, then you're going to evaluate the original function at the endpoints of the interval along with any critical numbers. So I'd evaluate f of -1, which is 1 minus 2 plus 3, which is 2. Then I'd evaluate f of 0, which is 0 minus 0 plus 3, so 3. I'd evaluate f of 1, which is 1 minus 2 plus 3, and that is 2 again, right? Yeah, 2. And then I'm going to evaluate f of 2. If I plug a 2 in, 2 to the 4th is 16, minus 2 times 2 squared is 4 plus 3. That's 16 minus 8 plus 3, which is 8 plus 3, or 11. Okay? So, all of these results here are going to help me determine what the absolute max and min are. The smallest number that you get is going to be an absolute min, and the largest number you get is going to be an absolute or global maximum. So I know here that I've got a global max when x is equal to 2. Okay? When x is equal to 2, or I could say at the point 211 if I wanted to. Okay? Because 11's the highest point in the function. And the smallest value, well, in this case we have 2 that equal the same, so I'd say we have a global min at x is equal to plus or minus 1, because they're equivalent. So generally there's one highest point in the world and one smallest point in the world, but every now and then you will get one where you have different inputs and you get the same output. And if that's true, we generally would say, you know, f of -1 equals f of 1, which equals 2 is a global minimum. Okay, pretty easy stuff, right? So that's what you need to know from section 5.1. Okay, you need to know how to find global or local extrema using the first derivative test. And that's it for this one. Talk to you soon.